So I decided to make a little video here for you guys, working through some homework questions. That way you can use it when you have your sub. Shouldn't take too long, so I'll work through these problems for you and you can see if you can follow along to help you for the test coming up. So number 5 is a biology problem. We've got a bacteria growing exponentially with that model, 80e to the kt, where t is the time in minutes. So if there's 80 cells initially, 675 cells after 30 minutes, find the value of k for the bacteria. So the first thing, you just want to kind of plug everything in. So 80 here is our initial amount, 675, that's the ending amount. So that would go in for my y. So we can set it up like this, 80e, and then we don't know k, we do know 30. So we usually don't write things like k times 30, so we're going to make that look a little bit better up there in the exponent. We're going to write 30k. And then we can solve for k here. All right, so we're going to find that gross value there. So let's divide by 80, because remember we need to get the e by itself. So 675 divided by 80 is 8.4375 equals e to the 30k. So now we have that number e there. Remember, we have to get rid of that because we want that exponent out of it. So in order to get rid of e, we have to take the natural log of both sides. That'll let me cancel that e out, and we're left with 30k. So the next step this would be written is natural log of 8.4375 equals, we have 30k. So divide the 30 out, and that will give us our value of k. So put that 8.4375 or that natural log in your calculator. Don't forget to close off your parentheses around the natural log before you divide by 30. And we get a value of k. That is 0.0711. So I'm just going to go to 4 decimal places here. I think I said 3 in class, but we'll go to 4 just to keep our answer as good or as best as we possibly can. So for B, when will the bacteria reach a population of 6,000 cells? So now we're going to use that value of k and solve for t here. So the ending amount is 6,000, and our initial amount doesn't change. We still have 80 at the beginning, and then we're going to have 0.0711 times t. The process here is exactly the same when we solve for t as we did for k. So divide the 80 out. So 6,000 divided by 80 in your calculator is 75. 75 equals e to the 0.0711 t. So we want to natural log both sides to get rid of the e. So the e is gone, and now we have natural log of 75 equals 0.0711 t. So divide by 0.0711 and we'll have our approximate value for t. Okay, so natural log of 75 divided by 0.0711. And I'm using a better value for k here, so yours might not be exactly like mine. It should be very, very close. So t is about 60.7331. And that is in minutes, okay, because we started with minutes here at the beginning. So after about an hour, we have 6,000 bacteria. So we went from 80 to 6,000 in about an hour. So that's pretty impressive. So down here on the bottom, the last one, I advised people to use Desmos to do this. I'll show you how to do it with math here. Okay, so if a second type of bacteria is growing exponentially according to that model, determine how long it'll be before the number of cells in this bacteria exceed the number of cells in the other bacteria. So we want this model here to exceed, so be greater than our original model. So we have to figure out when or what point in time they're going to be greater. So remember, we need to solve for t here. So in order for us to do that, we're going to have to use some natural logs again. But we need to natural log both sides right away. So we have an exponent with a variable up there. Let's natural log both sides right away. And then we have to think of what can we do, actually not there, what can we do right here? Can we separate that at all? Yeah, we can separate that with our addition property or our multiplication properties. This would be natural log of 35 plus natural log of e to the 0.0978t, and we do the same thing on the other side. So natural log of 80 plus natural log of e to the 0.0711t. So then the natural logs will cancel out with those e's, and we have to do some math to rearrange some things here to solve for t. So remember when these natural logs cancel out here, then we're just left with the exponent. So we don't really need to worry about those anymore. So we have natural log of 35 plus 0.0978t is greater than natural log of 80 plus 0.0711t. So what you want to do then is you need to put the natural logs on one side here and then the variables on the left, or wherever you want to put them. So I'm going to move this 0.0711t to the left, and I'll subtract it from that, and then I'll subtract the natural log of 35 to the other side. Okay, so right here is my inequality sign. So I'm moving stuff around. So on the left, when I do these two, I will have, that'll give me a 7, that'll give me a 6, that'll give me a 2. So 0.0267t is greater than, we have natural log of 80 minus natural log of 35, and you can leave that there until the end. I guess you could probably do it right now if you wanted to. But then we're going to divide by 0.0267t, or not t, excuse me, just the 0.0267 on both sides. So then we're going to put this stuff in our calculator and see what we get for an answer. So t has got to be greater than, all right, we got natural log of 80 minus natural log of 35. Enter, divide that by 0.0267. And we get 61.88. Okay. Two, 3. So that would represent our years. All right. 7 is a paleontology problem, so that's working with bones and stuff like that. So we got a bone that they think is 85% of that of the original found in living bone tissue. So we need to use that value of K that we learned today for carbon-14 dating, so 0.00012. And we know that we have 85% left, so that'd be 0.85 equals 1, which is the original, e to the negative 0.00012t. So remember, we're using 1 right there. That's how much you have originally. It's not stated in the problem, but you assume that you state with 100%, and then we're left with 85% after a certain amount of time, which we got to figure out. Okay? So remember, dividing by 1 isn't going to change the problem, so we natural log both sides. I'm just going to reuse that 1 as a natural log. So cancel out the e, and we now have this. Natural log of 0.85 equals negative 0.00012t. So then we're going to divide by that negative number there, and then put it in our calculator. Okay, so we're going to get t is approximately natural log of 0.85 divided by negative 0.00012, 1,354 years. And we'll just go to the fourth place here, 3244. Don't forget your label. That's important because we need to know if we're working with years or minutes or hours or what we're working with. Okay, most of the time with these types of problems, we'll be working with years. But then when you get to population models, you could be working with minutes if we're thinking of bacteria or something like that. Number 8, anthropology. So this is more bones. So an anthropologist has determined a newly discovered human bone is 8,000 years old. How much the original amount of carbon-14 is in the bone? Okay, so the 8,000, we found the bone and we think it's 8,000 years old. Okay, so that would be our time. We don't know A or Y, I guess we can call it Y. We don't know the Y value. We do know our original amount is 100%. We got E, and then our K value again is this, and our time is 8,000. So this one is essentially just plugging everything into your calculator to see what you get. Okay, so I'm just going to do E to that value in my calculator. So E to the negative 0.00012 times 8,000. And that gives us about, change it to about 0.3829. So that's Y. So if we want to write this as a percentage, which we probably do here, it's about 38.3% of carbon-14 left. Okay, so it's about 38.3% of the carbon-14. So that one's pretty much just plug and chug, throw the numbers in the formula, and see what you get. All right, so here we have a radioactive decay problem for number 10. We got 100 milligrams of uranium-238. They're stored in a container. It has a half-life of about 4.47 billion years. After how many years will we have only 10 milligrams present? Okay, so first of all, we don't know this value. We don't know what our K value is. Okay, you got to find that. But we do know we got 100 milligrams starting out. We also know it's got a half-life of 4.47 billion years. That's the information that we can use to find the value of K. So we start with 100. Okay, plugging stuff in. E to the KT, or T is 4.47. So we'll do 4.47 times K. That's what we're trying to find. If we know that this information right here tells us our half-life, you got to think of the concept of half-life. How much is left after that certain amount of time? It'd be half of it. So we started with 100, so that means half of it would be 50. So this equation right here is the one that we have to use to figure out K. So let's do it. Divide by 100. So 50 divided by 100, that's half, 0.5, right? That's the way it should work out because it's half-life. E to the 4.47 K. So what do we need to do to both sides here to get the E gone? Natural log. Natural log both sides. The E is out of here. So now we have natural log of 0.5 equals 4.47 K. Divide by 4.47, and that will give us our value of K. So K, and I'm going to kind of save that number in my calculator. I do natural log of 0.5 divided by 4.47. We get about negative 0.1551. Okay, that's half the battle there. So now we need to figure out how long it's going to take for our 100 milligrams of uranium-238 to turn into 10 milligrams, okay, because it's half-life. It just keeps breaking in half and in half and in half. You could do a lot of work to figure that out, but you wouldn't get an exact number is what we're looking for, okay? So, new equation here. We started with 100 milligrams. We have E to the negative 0.1551 T, because T is what we're trying to find. And we're looking to figure out how long it takes for our 100 to turn into 10. So divide both sides by 100. And this is 1/10 on the left, or 0.1, equals E to the negative 0.1551 T. So now we need to natural log both sides again. That gets rid of the E. We got natural log of 0.1 equals negative 0.1551 T. So divide that out. And then we can throw that puppy in our calculator and we'll get the answer. So T is approximately natural log of 0.1 divided by that K value, 14.849. And if you read through the problem, it's not 14.849 years, it's 14.849 billion years. So that would be 14.849 times 10 to the 9th, if you were thinking our actual number. Okay, so 14.849 billion years. So we found our K value. We used the K value to find a value of T for when our radioactive uranium will turn from 100 to 10 milligrams. Okay, one more problem here. So number 10, got population growth. Okay, population of the state of Oregon has grown from 3.4 million in 2000 to 3.9 million in 2012. Write an equation in the form y equals a times e to the kt for Oregon, where t is the number of years after 2000. Okay, so we need to figure out our growth factor here, or our growth rate, which is k. We don't know that, so we can't technically give an equation until we know that. So let's figure it out. So we have two values up above, 3.4 million in 2000. Let's call that our starting amount. Okay, that'd be my A. E to the kt, we don't know that. Let's throw a little bit more information in there. So my ending amount is 3.9 million. And then we now have a value for t because 3.4 was in 2000 and 3.9 was in 2012, so that is 12 years. So we have 12k up above, and now we can solve. So divide by 3.4 on both sides, and then you're going to use your wonderful natural log to get that exponent down. So 3.9 divided by 3.4 is 1.1471. So that's going to be equal to e to the 12k. And then we need to natural log both sides. Okay, and from there, that cancels out. We got natural log of 1.1471 is equal to that exponent that we had left over there, 12k. So we just want to divide both sides by 12, and we'll get our value for k. So, and I am using the exact answer here, so I'm not really rounding in my calculator. So your answer may be slightly different from mine, okay? Because I'm using not just 1.1471, I'm using the exact decimal in my calculator. So when I do that, I get k is equal to 0.01, oops, excuse me, 0.1 4. And you could keep going if you wanted to, but we're just going to go to 4 decimal places. So we don't actually have the equation yet until we write it out with the k in there. So we get y equals a, which is our 3.4 million, e to the k, which is 0.0114, times t. So this is the equation here that we need, because we want to generalize that so we can plug stuff into it. Okay? So use your equation to predict the population of Oregon in 2025. So that should be pretty simple after we have that equation there. So let's just plug in our value for time. So we got 3.4 e to the 0.0114 times t. So how many years to get to 2025 from 2000? That's 25 years. Make sure that you're doing the stuff in the exponent first. Okay, so we'd have 3.4 times e to that value. And my exact value here, if you're not using an exact value, you should be something fairly close to this. 4.52, we'll just say 50 if we round up. Okay? And that would be our population. So that would stand for millions of people. Okay, so we got about 4.525 million people. All right, one more step to this problem. According to the equation that we have written above, up here, when will Oregon reach 6 million people? So we have an ending amount now of 6 million people. That's what we're trying to find, the time for that. So we got 3.4, which is the original. We got e to that value. and then we're trying to find t. So just like all the other problems that we've done here, get the e by itself, and then you're going to natural log both sides. So 6 divided by 3.4 is 1.7647. Okay, and you can round that if you want to, but I'm going to use the exact value in my calculator again. So e to the 0.0114t. So I'm going to take natural log of both sides here. That's going to cancel out, and I'd have that 0.0114 up there. So I'm just going to kind of be a little lazy rather than rewrite it here. I'm just going to divide it out from both sides and get the number in the calculator, 0.114. Okay, so we will take natural log of that 1.7647, and we're going to divide it by 0.0014, and we get t is about 49.6775. Okay. So remember again, you should get something close to that. So it should be 49 point something. I used exact values in my calculator. I didn't round anything until the end here. In class, I rounded a little bit because I wanted to keep up with your guys' calculators. I used a different calculator tonight, so I could use exact values the whole way through. But that is all the questions for you. So you shouldn't really have any homework questions to work through. Make sure that you do this and write down the proper amount of work. Don't just scroll through the video and write down the answers, okay? Hopefully this helped out. There's a lot of the same concepts here, especially when we get to natural logging both sides. That's how we get an exponent down out of the power there, okay? So hopefully this helped. Good luck on the review guide. Have a great day.